nice paper by Wayne Hayes, who was actually a former student here in computer science, who integrated the solar system using a mixed variable symplectic method, a very high order standard multi-step method, and some incredible method I'd never heard of, which in which you did a Taylor series expansion of the equations of motion to like 40th order by computer algebra. And then you had these really long terms, but you could use time steps that were a factor of 10. You could use time steps of like half a year, factor of 10 bigger than you could use with. Anyway, so he did all these. He did them in double precision, extended precision, and he was able to show that if you really did all the integrations of all the different methods accurately enough, you got not exactly the same behavior, but you got exactly the same Lyapunov enough times, and the same variation of Lyapunov enough times with small changes in initial conditions. So it has been looked at, I would say, much more carefully than I would have the patience to do.
Is it mathematically correct to switch, use multiple integrator in a simulation? For example, for close encounter, to use some highly accurate integrator, and then for long run, you just use the big flow synthetic integrator for long run. Is it possible to switch between different integrators?
Well, of course, as soon as you switch, it's not symplectic anymore, because any decision that's based on the position in phase space makes it not symplectic. So all you can do, I think, is test things, and if you test things well enough and they behave well enough, then they're okay. But technically speaking, as soon as you're doing a switch like that, you don't have a symplectic integrator anymore.
So the only way we can test is to add up the energy error and see if they are well behaved.
Well, the energy error is not necessarily a very good test, because the energy in the solar system is dominated by Jupiter. Mercury could be completely wrong and your energy error would be fine. So the only real way to test is to do it twice with two different step sizes and see if you get the same answer. If it's chaotic and you integrate for many Lyapunov times, you won't. And then I think it's safe to say that we have no good theoretical basis for understanding whether the calculation is accurate or not. People who believe in symplectic integrators will say, oh, everything's fine because everything's a Hamiltonian system. So, you can take that argument with whatever credibility